All right, so again, just a couple reminders for anyone who is watching the video. So this week we won't have our test on Friday because of the 2 half days with conferences. We'll start the test if you're in period 2-3. We'll start the test on the Tuesday next week, and then we will finish it on the Wednesday. If you have a full class on the Wednesday, or if you're meeting with me that last period, that'll be about an hour on the Wednesday. So we'll probably have enough time to do the test just in that day on the 24th. But if we have time, we could also start it on the 23rd. All right, so I'll update that as the week goes on. All right, so let's take a look at an example where we're going to rewrite an expression just using properties of exponents we already know. Okay, just remember, things like if you're multiplying with the same base, you add exponents. Power to a power is when you multiply. If you're dividing things with the same base, you subtract exponents. Okay, so let's look at an example that just kind of goes through those properties. So they've given us an expression that says a to the 2x plus 3y minus z. And when we're done, we want to rewrite that in terms of just a to the x, a to the y, and a to the z. All right, so let's start with this part. Somehow you had something before that that would have caused you to add exponents together. So what's the rule? I think I just mentioned it, but what's the rule when you have to add exponents? What would have come before you simplified it to that step? Michael?
Wouldn't it be a to the power of 2x times a to the power of 3y?
So we would have had, a to the 2x times a to the 3y. Okay, that takes care of what's in the box. Now, what about the minus z? What would have caused us to have to subtract in an exponent? Yep.
Isn't that just division? So you divide by a to the z power?
Yeah. So we would have had divided by a to the z. Okay, so we've got the bottom all set. That's the way they want it. Okay, just in terms of a to the z. Now, we still have a to the 2x and a to the 3y. What's another way we could write a to the 2x in terms of a to the x? Like something you could do to a to the x to turn it into a to the 2x. Nick?
2a raised to x.
2a raised to the x, like that?
Oh no, just the a raised to x.
Just the a raised to the x, like that?
Yep.
So that would give us this. That would just give us 2 times a to the x. It wouldn't give us a to the 2x. So we've got to do something that's going to keep that 2 up in the exponent. Yep?
Would it be a to the x and then the parentheses to 2?
Yeah, so that would be a to the x squared. Right? So now you've rewritten that in terms of a to the x. We could do the same thing with a to the 3y. So we take a to the y and cube it. Now we've written that in terms of a to the y. And the bottom is already written in terms of a to the z. All right, so just an example that kind of goes through, kind of summarizes all those different rules of exponents. But any questions about rewriting that in terms of a to the x, a to the y, and a to the z? All right. So we've done a lot of exponential growth and decay problems, but the way we've always had to solve them was using the calculator. Right? So we would usually put something in y1, put something in y2, and then see where they cross. Well, we're going to look at a problem that we've already done before. I think it's about the population of a town starting with 50,000 people. But this time, we're going to solve the same problem we've already done, but we're going to do it algebraically, okay? Instead of using the calculator. So I'm not sure the exact section we did this in. It might have been 5 point, I think it was 5.1. And so we have a town with a population of 50,000 people, increasing at a rate of 2.5% per year. And I think they asked, how long will it take the population to double, if I remember. Yep. How long will it take to reach 100,000 people? All right, so first thing we're going to have to remember is what our formula is for exponential growth. Then once we have it, we'll fill in all our values, and then I'll show you how to solve it algebraically. And as a reminder, we could solve it graphically first, just to see what the answer was that way, and then make sure we get the same thing now when we do it algebraically. All right, so what we're going to have is a formula for the population as a function of time. Anybody remember when you write down your formula for exponential growth, what's the first thing that you put in the formula? Yeah?
Isn't it the starting population?
Yep, it's always the initial amount. It's always what you're starting with, times, and then it was something in parentheses. Anybody remember what went inside the parentheses? John?
Is it rate?
Part of it. It's part of what goes inside the parentheses. Lindsay?
1 plus rate.
1 plus my rate. If it was decay, it would be 1 minus my rate. So 1 plus, and what's going to be the rate that I put in here? Michael?
0.025.
0.025, right? We've got to make sure we put it in as a decimal. 0.025, and that's raised to the t. All right, so let's just simplify that a little bit. 1.025 to the t. And they want to know when we are going to reach 100,000. So where would that 100,000 go? P of t or t? Which one would it go in for? Yeah, Kip?
P of t.
Yeah, it's going to go in for P of t because that's a population. It's not a time. It's not 100,000 years. That's 100,000 people. All right. Okay, so we got that. Let's just graph it, just to remember what the answer was, and then we'll do it algebraically. So we've got 100,000. We've got 50,000. Times 1.025 to the x. Let's see, minimum amount of time. Usually that's 0. Can't go negative. How many years is it going to take? Let's say it was 20-something years. Let's just go out to 35 years. Minimum population. What's the minimum the population would ever be in this model? Yeah.
50,000.
50,000 because it's increasing, it's not decreasing. Or if it is decreasing, this growth rate takes that into account. Maybe it's increasing at a rate of 4%, but people are dying at a rate of 1.5%, so overall it's still increasing. All right, so 50,000, this is the minimum. We want to know when we're going to hit 100,000. So let's do 110. Yeah, so there's our line at 100,000. Yeah, I probably didn't even need to go all the way to 35, but let's see what we get. Okay, so now, what do I need to calculate there to get that answer? Intercept. Okay, so this is the way we did it back in 5.1. We get 28.07 years. All right, so we've done that before. All right, so now I want to look at solving for t algebraically. What makes it a little bit harder to solve for t than like an equation you'd see in Algebra 1? Yep, Lindsay?
It's in the exponent.
It's in the exponent. So we talked about something last week that deals with exponents and ways we can rewrite an exponential expression so it's not in an exponent anymore. Okay, we'll get to that in a second. But there is at least one thing here I could put on the other side before I have to deal with changing this from exponential form. Does anybody see something we could move from the right side over to the left? Nick?
50,000.
We can move the 50,000, and how would you move that over?
You divide it.
Yep, so we're going to divide it. And divide it. 100,000 divided by 50,000 gives me 2 equals 1.025 to the t. So not a very long equation. The only thing that's a little tricky is having the t as an exponent. Now, the next part is a little tricky, so I'm going to have to give you a hint. But I'd like to be able to take this t and move it somewhere. Where did we say last week, if you have an exponent, you're allowed to move it where? But you can only do this if you have a certain function in the problem. That'll be my next question. So where are you allowed to move that t? Lindsay?
In the front.
You can move it to the front. But what do you have to have in the problem to be able to do that? You can't just take the t and just put it in front the way it is right now. Yep.
Log.
You have to have a log. So that's what we're going to do. We're going to introduce a log into this problem. And we're going to take the log of both sides. You can do that just like you could take the square root of both sides. Okay? As long as you do the same function on both sides. So log of 2 equals log 1.025 to the t. Now, I didn't write the base that I was using. I could take the log of any base on both sides, as long as I use the same base. But since I didn't write the base, what log base am I assuming? Yeah, John? 10. Okay, we could have done the ln on both sides, but log is just the simplest. Now, you can take the t and put it in front. So now you have log 2 equals t times log of 1.025. Now the last step is to get t by itself. What would be my final step to get t alone? Yeah, Caleb?
Divide each side by log 1.025.
Yeah, this is just like having 2 equals x times 4. If you want to get the variable by itself and you have multiplication, just divide by the number that's next to the variable. What is the log of 1.025? I don't really care what it is at this point, because I'm just going to type that in and get a final answer. So divide by log 1.025, log 1.025, and that should be your answer for t. Let's check and see. All right, so we get log 2, make sure you do close that parenthesis, divided by log 1.025. We get 28.071, which is exactly what we got when we solved the graph. Right, and after we do a couple of these, there's even a quicker way to do it. And you might just start to even notice the pattern here. When you have something in that format, you're pretty much just going to take the log of the number that's by itself and divide by the log of the base on your exponential expression from the right-hand side. That's the pattern that happens pretty much every time. Any questions on that? Okay, so now we should be able to solve these types of equations without having to graph them. Whether it's an exponential growth or an exponential decay formula, that doesn't matter. It would just change the 1 plus to a 1 minus. It doesn't really have any effect on the steps you would take to solve it. Okay, so I think this is the last thing in this part of the section. Yeah. So algebra 1, sometimes you talk about scatter plots and you have different points, and you try to find a line that fits those points perfectly. Right? So maybe something like this. And there is a formula, and if you take statistics, you'll learn exactly what the formula is to find what's called a line, not only a fit, but a line of best fit. It means it's mathematically the most perfect line that you could have to go through these points, minimizing how far away it is from every single point. Okay, the minimum distance, minimum what they call residual from each point. And line of fit is great if you've got points that are following a pattern that looks like a line. But if you had something where your points looked more like that, and you try to fit a line to it, it's not really going to be a good model for the data. Okay. This kind of data, at least to me, looks more like you'd want to try to fit a curve to it. Okay. And we're going to look at how we can find what's called a power model for a set of data. Right. So first thing we have to kind of learn is that sometimes a power model isn't the right tool to use. So we're going to have to figure out, okay, I have a set of data. Is this data that I should try a power model on? And if it is, how do I get the model? How do I get the equation of the curve that will go through those points the best that it can? Right? And that's where the graphing calculator is going to help us out. So we're going to be finding equations that look something like this. It's almost like a one-term polynomial. That's basically what a power function is. The difference, the reason I can't really call it exactly a polynomial is because sometimes this exponent is a fraction. In polynomials, you never have a fraction as the exponent. So an example of a power model could be like y equals 3x to the 2/5. That's an example of something that could be a power model. So kind of like a one-term polynomial, but the exponent could be a fraction. But that's what your answers are going to look like, and the calculator will basically calculate the a and the m for us automatically. The a is the number that's in front of the x, and the m is the exponent. Now, the calculator might use different letters besides a and m. It doesn't really matter which two letters you use. Just when the calculator gives you the answer, it'll show you what it's calling these two letters. Just make sure you copy the numbers they give you in the right spots in that formula. Okay, but it's going to give you the two things that are circled, okay, whatever the calculator calls them. Especially if you have like a Casio or a different model, it may use totally different letters than my calculator. All right, I'm not going to do like that. Okay, so how do we determine if a power model fits data? Not everything is a power model. Some things are, some things aren't. What you want to do to see if your data represents a power model, look at your x and your y values, take the ln of every single number in the table. You're really not going to have more than probably 8, maybe 4 x's and 4 y's. But take the ln of every number in the table and graph those points. If those points look like they're in a pretty straight line, then that means a power model is a good thing to use to represent your data. Now, I'll show you another way around that. You technically don't have to do that. What you could use, and most people, I don't have this, but on the computer I do, you could use what's called logarithmic graph paper. Yeah, I don't really want to spend too much time looking at that because I'm just going to have people do it this way. But if you use what's called logarithmic graph paper, you could plot the points the way they are. You don't have to take the natural log of them and see if they're in a straight line. Okay, so I'll show you both ways, but this is the way we're going to stick with because you're not going to have access to logarithmic graph paper most of the time. Okay, so if it looks linear, then we'll go on to step 2. If it doesn't, we would stop and say a power model is not a good fit for the data. Okay. So, next step. We're going to find, what did I call it? Hold on one second. We're going to find, let me just change the letter to the letter that I used. Y equals, I didn't call it B, I called it A. Sorry. Okay, so we're going to try to find A, which is going to be the number that's in front. Then we're going to try and find M, okay, which is the exponent. And then your final answer is going to be in the form y equals A times x to the m, I think is what I wrote. Yeah. Let's try to find A, we'll try to find M. We'll go through how to do that, and then we'll write our final answer. And the A and the M are pretty much, they're going to be given to you on the calculator at the same time. So there's not really going to be anything we're going to do by hand for that. All right, let's go through an example. So there's our data. So the first part says determine if a power model is appropriate for that data, and then if it is, go ahead and find the model. Okay. So let me graph these points on what we call logarithmic graph paper. It's not a graph paper that I really use at all, more than once a year. So I'm going to look at it and see if I can remember how it works. Okay, and this will probably be the only time that I actually use log paper to show you how to do this. Okay, and I'll put those points back up in a second. All right, so let's see. All right, so your regular graph paper, that looks like do I even have regular? Yeah. Okay, so there's regular graph paper. This is log graph paper. So it's a little bit different. And the scale on it isn't consistent. Let's just pick a starting point. Let's start right here. So, if I remember correctly, the way that log graph paper works, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now it goes by tens. So this is 20, 30, 40, 50, 60, 70, 80, 90, 100. And then from there, it goes by hundreds. And what logarithmic graph paper does is it makes things that would normally look like a curve look straight. Specifically, things that would look like a logarithmic curve. They'll look perfectly straight on this graph. And what that has the advantage of doing is then you can kind of think about your graph as having a slope and a y-intercept. Where normally when you have something that curves, we don't think about it as having a consistent slope because it's curving, so the slope is always changing. This makes it look consistent. All right, so again, I'm going to show you quickly those points, but then I'm going to show you how to do it without this kind of graph paper. All right, so we've got the point 1, 5. People can tell me the points, that would be easier, so I don't have to keep switching. But 1, 5. All right, so we've got, let me label, the y-axis has the same labels, but what I should probably do, because the y values are going to go up quite a bit higher, let's put those down there. And let me zoom out a little. Okay, so what was the first point? 1, 5?
Yeah.
Okay, so that's 1, 2, 3, 4. 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. All right, so 1, 5 is right there. Okay, what's the next point?
331.2.
331.2. Okay, I might not be able to fit them all on here, but I'll be able to get most of them. So 3, and then 31.2. 20, this is 30. So just above that. So 31.2. Okay, and what's the next one?
573.1.
Okay, I can still get that one. So that's 30, 40, 50, 60, 70. And it was 573.1.
Mm-hmm.
Okay. 5, let's go up to 73.1, about right there. I think that's the last point I'm going to be able to fit, because the next one's like 160, right?
Mm-hmm.
All right. But hopefully you can see, at least for the 3 points that I did, it does look like they are pretty close to a straight line. Okay, it's not perfect, but they are pretty close. So logarithmic graph paper makes those points look like they are in a straight line, which means a power model is a good fit. Now, let's say you don't have logarithmic graph paper. That's fine. Let's take the log of all these numbers in the table instead, and then graph it on regular paper, and you can get the same result. All right. So, I think, since I already know this is going to be a good fit for the data, I'm going to show you how to take the ln of all these numbers very quickly, okay, without having to type them all in. ln of 1, ln of 3, okay, that's going to take a while. So what we're going to do is we're going to press Stab, we're going to go to Edit, and we're going to type in these numbers. If you already have numbers in the table, you can do what I'm doing right now. Highlight the number you want to delete, and then press Delete. All right, so let's put in 1, 3, 5, 8, and then go over to column 2, put in your y values. So we've got 5, 31.2, 73.1, and 160. Okay, any questions on typing those in? All right, now, if you did it the way I did it, my x's are in L1, my y's are in L2. If you go back to the home screen and you press second 1, you get this thing that says L1. If you hit enter, it's going to show you the numbers that are in L1. 1, 3, 5, 8. So what I'm going to try, and I think this is going to work, is I'm going to press the ln of L1. Now what that's going to do is take the natural log of every number in the list without me having to press ln 4 times. And it's going to give them back to me right on the screen. Okay, I'm going to have to scroll to the right because it's giving me decimals, but that's fine. Here's my lnx, lny table, which is normally how you guys are going to check if a power model is a good fit, because you're not going to have logarithmic graph paper to do it. So, we get 0. We've got 1 point, again, we're graphing this, so really rounding to the 10th is fine. You're not going to be able to graph more accurately, and you just want to see if they look like they're in a straight line. So let's go 1.1. 1.6, and the last one, 2.1. Okay, there's the ln of all the x values. Now the ln of all the y values. So let's go ln, second, 2. We'll take the natural log of everything in L2. If you didn't put your y's in L2, then you need to put L3 or whatever list you used. But I used L2. So we get 1.6. We're going to get 3.4. We're going to get 4.3 and 5.1. Now, you've taken the natural log of everything in the table, plot that on regular graph paper, and see if it looks like they are in a straight line. If they are, then we'll go ahead and write down the power model, which is easy now that we have all the data typed in. Okay, we just have to press a couple buttons. All right, so let's take this kind of graph paper and plot the points. 0, 1.6, 1.1, 3.4, so 1.1, 3.4, about like that. 1.6, 4.3, 1.6, 1, 2, 3, 4.3, and 2.1, 5.1. So 2.1, 1, 2, 3, 4, 5, and then up a little bit more, right there. Okay, and let's put a line and see if it looks like they're pretty close to it. Okay. Does it look like those points are pretty close to a straight line? Yeah. If the points looked like this, let's say you had something like this, now then I'd say, no, those don't really look like they're going to be in a straight line. So a power model would not be a good fit. And if the question was find a power model if appropriate, you'd say it's not appropriate and just stop. All right, but it does look like it's appropriate here. So now let's go ahead and find it. Okay, once you have your data in, you're going to press Stat. And this time you're going to go to Calculate. And depending on what you've typed in, you can calculate all kinds of things with those numbers in the lists. What we want to calculate is a power model. It's towards the bottom, and the quickest way to find it is actually to go up. And then it'll put you at the bottom of the list. And on my calculator, it's option A. It's called a power regression. That's what we're finding. Okay, a regression is a calculation that fits a curve to data. We want to fit a power curve to data. That's what we're doing. Yes?
Where did you get that?
If you go to Stat, and then you go to the second menu over, which is Calc.
Okay.
Now, once you highlight option A, you can hit Enter. It's going to ask you a couple things. If you haven't changed how you did it from what I did, you can do exactly what I'm about to do. My x's are in L1, and my y's were in L2. That says L1. Try to see if I can. I can't grab it. But yeah, x's are in L1, y's are in L2. If you used a different list for your x's or y's, here's where you could change it. Let's say you put your x's in L6. I could press second 6. Okay, my x's are not in L6, they're in L1. So I'm going to put my x's in L1, my y's in L2. We don't need to change anything about where it's going to store the regression equation. That's just a place on the calculator that you could store it later on if we want to use it. We don't need to store it, we're just going to look at it on the screen and write it down. So all we have to do is go to Calculate, take a blink, and it should give you something like that. So the number in front of the x is 5, and the exponent, well, that's 1 2/3. Okay, so we're going to just round that. 1 2/3 would be what, 5/3? So we'll just round it off to 5/3. And that's it. That's all you have to do to find a power model. I'll graph it just to see if it, how good it looks. But let's write it down. So y equals 5x raised to the, again, that's 5/3, because I'm assuming really it looks like it's 1.6 repeating. But because the data isn't perfect, that's why these numbers aren't quite perfect. But A should be 5, and B should be 5/3. So again, not quite a polynomial because you have a fractional exponent, but pretty close, just a single term, and that's our power model. Now, this part you guys can just watch. You don't have to actually do this part, just kind of watch what I'm doing. What I want to do is look at these points on the screen. So my x's go from 0 to, or 1 to 8. Let's do 0 to 10 on my x values. And my y's go from 5 to 160. Let's go 0 to 200 on the y's. So 0 to 200. Now, I'm going to clear out anything else I had, and if I hit graph, I don't see anything. I should be seeing points. Well, the reason I'm not seeing any of these points is because I didn't turn on a scatter plot. Okay, so if I want to actually see what those points are, I have to go up to plot 1 and turn it on. Now, I know my settings in plot 1 because I'm the only one who uses this calculator. But if you're not sure, well, what's plot 1 actually doing, you can press second y equals, and it'll show you what plot 1 is doing. So plot 1 has been turned on. The type of graph for plot 1 is going to be a scatter plot. Okay, I could do a line graph or a bar graph or a box and whisker. I can do all kinds of things, but I just want to do a scatter plot. I want it to get the x's from L1, the y's in L2. I don't really care what kind of mark it uses on the screen. I mean, just the dot would be fine, but it's going to do these little squares. And it's going to do them in blue. I don't really care about that. So there's nothing that I need to adjust in my scatter plot. Okay, but if I needed to, second y equals is how I could adjust it. So all I did on the y equals screen was I went up to plot 1 and I turned it on. And if I hit graph, I can see those points that we typed in now. And now I'm going to type in the equation we just found. 5 times x to the 5/3? Yep, 5x to the 5/3. This is purely just to see how good the curve looks. That's all I'm checking. 5x to the 5/3. Looks pretty good. So that's a curve that models that data. Now from there, I could say to you something like, well, if x was 1.3, what would you expect y to be? Well, you have a formula now that you could plug 1.3 in for x, and you could solve for y. So that would be called interpolating, predicting a value between two that you already know. Or I could have you what's called extrapolate from there and say, what if x was 6? What would you expect y to be? Now, the further you try to predict from your actual data, the less reliable it is. Okay, because we don't know if that trend is going to continue. We know that it works for these 4 points. That's all we know. Okay, so any question on determining if a power model is appropriate, and then how to find it on the calculator? If you forget, like for the homework, you can always just go back, look at the video, and see the buttons that I pressed again. Okay, because that'll be in the video. All right. So, last thing we'll finish up with is looking at some graphs of logarithmic functions. Now, what are the 2 bases that we've dealt with so far? Or put it this way, what are the 2 bases that the calculator can do for you automatically? John, can you give me one of them?
Base E.
Yep, it can do base E. That's the LN button. And what's the other base it can do? Yep. It can do base 10. If we go back to the problem that I had you guys solve algebraically, right here. One thing you could have done at this step was to try to change your equation from exponential to log form. The reason I didn't have you do that is because you would have ended up with something like this. Start with your log. The base on your log is the base from the exponential. Logarithm always equals the exponent. Seems fine, right? Perfect. We get the exponent all by itself. That's what we were trying to do. And here, the 2 is called the argument. Remember, it ends up alone because it annoys everybody. So that goes right here. So there's the answer. Without actually having to do kind of this step in the middle of taking the log of each side and then moving the t to the front. This is the calculation you ended up doing. Log 2 divided by log of 1.025. That's exactly how you type that into a calculator. That's a log that's a base besides 10 or e. So the only way to type in, unless you have a special feature for it, the only way to type in a log with a different base is to take the log of the argument, and again, I'm going to write this down on the next, when I show you the formula nicely, and divide by the log of the base. That's exactly what everybody typed in when we did this problem. It just took us a little longer to get to that because we took this extra step of taking the log of both sides and then moving the t in front. But we don't have to do that. We can use what's called the change of base formula and jump right from this equation to the final step without what's in the middle. Bless you. So the change of base formula says if you want to take the log base b of x, and b is not a 10 or an e, the way you type it in, there's actually 2 ways you can type it in. You can take the log base 10 of the argument and divide by log base 10 of the base. Or you could take the ln of the argument and divide by the ln of the base. You're going to get the same answer no matter which way you do it. Okay, let me go back to the problem we solved algebraically. Let me type it in as an ln. So we got, what did we get? 28.07. Let me type in ln2. So ln of 2 divided by ln of 1.025. 1.025. It's exactly the same answer that we got. Okay, so what I usually do is just pick one way to remember to do it and just do it that way. I usually do log base 10, but if you want to do ln, that works as well. Okay, so let's see if we can graph something. And now it doesn't necessarily have to be a base 10 or base e. Okay, we just type it in however we need to get it in y equals. And I want to graph log base 3 of x. So, can somebody give me a way that I can rewrite that so I can type it in on my calculator? John?
Never mind.
Caleb?
ln x over ln 3.
Yep, that's one way we could do it. ln x over ln 3. So I've just converted it from something that I don't have a button for directly to something that I do. Now some calculators have special features built in to deal with that. I'm not going to assume because I don't know what kind of calculator you have. This will always work. No matter what brand, whatever you've got, you don't need any special feature. Just type it in just like that. All right. So So ln x. I'm also going to turn my scatter plot off because I'm done with that. I don't want to keep seeing those points. So let's do ln of x divided by ln 3. And let's do zoom 6. And remember that this graph really should look, let me show you. Like that. That's how it should look. Because all log functions have a, what kind of asymptote here? Vertical or horizontal? Michael?
Vertical.
They all have a vertical asymptote. Okay? If you don't shift it, well, that's what we're about to figure out right now. What's the domain here? Yep, Nick?
0 to infinity.
Including or not including?
Not including.
Not including.
Either.
Cannot take the log of a negative number. We talked about that. The base on a log can't be negative. The argument can't be negative. So 0 to infinity. And how about my range? What's my range going to be here? Yep.
Is it negative infinity to infinity?
It is negative infinity to infinity. Remember, logs are extremely slow growing. So if you get all the way out, say 100 on the x-axis, you're going to have gone up 2 on the y, because the log of 100 is 2. So it's very, very slow growing. But that's it. So we wanted complete graph, domain, and range. That's good. Questions on that? All right. All right, so transformations. All the transformations that we know, again, for the 4th or 5th time this year, are exactly the same as what we've done. So again, I'll say them quick, but we're not going to go into super detail. What does A do? Adding or subtracting inside the log function. Sophie?
Horizontal shift.
Horizontal shift. How about B? Multiplying inside the log function. Michael?
Horizontal stretch.
Horizontal stretch. What if B was negative? What would that cause your graph to do? Yep.
Horizontal reflection.
That'd be a horizontal reflection. You could also say reflection over the y-axis. Now we're going to get outside the log function. C is multiplication, but on the outside. What does multiplying on the outside of the function do? Lindsay?
Vertical stretch.
Vertical stretch, and if C was negative, it would also cause a vertical reflection. And lastly, D, so we're back to adding. This could also be subtracting. What does D do to our graph? Yep, Mass.
Vertical shift.
That's going to be a vertical shift. Positive is up, negative is down. On the horizontal, it's backwards. Positive is left, negative is right. What else? With C, if you multiply by a big number, it stretches the graph vertically bigger. With B, if you multiply by a big number, it actually compresses it. So if you had something like log 3x, just keep it simple, that we would describe as a horizontal stretch by a factor of 1/3. If you had something like this, log 1/4 x, that's a small number. That's actually going to stretch it bigger. It's the opposite. So I would say that's a horizontal stretch by a factor of 4. Okay. All right, questions on the transformations? All right, so let's see how we could get the graph of log base 3 of negative x from the graph of log base 3 of x. The bases have to match. Okay, that's always the comparison between logs with the same base. All right, so how many transformations are happening to turn what's in green to what's in blue? John? Just one. There's only one transformation that's happening. Can you tell me what the one transformation is?
No, it is being flipped vertically? No, it's being reflected towards.
Which one do you think?
Reflected horizontally.
Yes, that's a horizontal reflection. You could also say reflect over the y-axis. So reflect over y-axis, or just say horizontal reflection. What else do they want? How do we graph it? Find the domain, the range, and the vertical asymptotes. Okay. Domain, range, vertical asymptotes. Well, if we know what the domain and range are for the one we just did, log base 3 of x, you are reflecting this horizontally. So it's going to look like that. So what's going to be the domain once we reflect it? Sophie? It's going to be negative infinity to 0. How about my range? Yep.
It's going to be negative infinity to positive infinity.
It's still negative infinity to infinity. You can't change the range of a log function. It goes up and down forever. So no matter what you do to it, it's still going to go up and down forever. And vertical asymptote always starts out with what letter? Yeah, x equals. And there is no change in the vertical asymptote because you reflected it right over the original vertical asymptote. Okay. If you shifted it left or right, you'd have to take that into account. Like let's say you have this. Now I would say the vertical asymptote there is at negative 3 because it's been moved 3 units to the left. Okay. So you just have to take that into account if you shift. If it starts to get confusing and you have a number like that, and you're like, I don't know what the vertical asymptote is now, remember, logarithmic functions only go in one direction. The smallest number that you can ever plug into a log function is 0. So set that argument equal to 0 and find out what x would be. And that'll tell you your vertical asymptote. Okay. So the vertical asymptote is whatever number you would plug in for x, and it would make what's in the parentheses come out to 0. So applying that to this, what would you plug in here to make what's inside the parentheses 0? 0. X equals 0. Okay. Any questions on that? All right. Okay, we'll just do the transformations quick here. It isn't written in the standard order we normally would like to see it. That's usually what we're looking for. Somebody tell me what the first transformation would be. Yep, Sophie. So shift left 3, like it, good. And the last thing. Yep.
The reflection over the y-axis.
Yep, reflect over y-axis. So now if I asked you what is your vertical asymptote in this one, I would do this. Find out what you would have to plug in for x to make the argument 0. And the answer is 3. So there would be a vertical asymptote at 3. So then your domain is either going to be everything above that or everything below that. If you're not sure, graph it and see which way it goes. Or think about the transformation, because you know which way it normally would go. And that transformation is going to make it go the other way. I think, yeah, last two. All right, so when we are graphing a log function, it's helpful if we can try to find the vertical asymptote, because that tells us which way it's going to curve. Basically, it's going to curve away from the asymptote, either left or right. And if we can find the intercepts, that's helpful. Not every log function is going to have a y-intercept. It will always have an x-intercept, because remember, it goes up and down forever. But it might not always cross the y-axis. Depends. So this is what I told you guys earlier. To find the vertical asymptote, you set the argument equal to 0 and solve. How do you find the y-intercept? What do you plug in? And what do you plug in? What letter do you plug that in for the y-intercept? Yeah.
The x equals 0.
Yep. To find the y-intercept, plug in 0 for x. To find the x-intercept, plug in 0 for y. Again, if you need some more points to graph it, that's fine. I would suggest using the table, but make sure you only plug in x values that would result in positive numbers. I would not plug in something like 2 for x in that log. That's not going to work. 3 is not going to work. 4 is not going to work. Greater than 4 is what you're looking for. Okay. So make sure the argument is always positive. And my graph paper goes out to 10, so usually if I have to pick, I'll be picking numbers between -10 and 10 for x. Okay. All right, so let's see if we can sketch this. Log base 2 of 3x plus 5. Okay, find the domain, the range, and the asymptotes. Well, log functions only have one kind of asymptote. What's the kind of asymptote that you always have in a log function? Yeah, it's just a vertical. Okay? And that's probably something I would find right away because I'm going to use that for my graph. Find out what you would have to plug in to make the argument 0. That's your vertical asymptote. So vertical asymptote is x equals -5/3. Now, can I plug in numbers larger than x, or do I have to plug in numbers smaller than x into that? I can only plug in numbers on one side of -5/3.
Larger.
Yeah, it has to be larger. Just pick one and test it. I think an easy number to test is 0. 0 is larger than -5/3. If I plug in 0, 3 times 0 is 0, plus 5 is 5. That's fine. Try a number that's smaller than that. Try -10. Well, 3 times -10 is -30. -30 plus 5, -25. No good. Okay. So that tells us our domain is everything larger than -5/3. Do not include -5/3. All right, so we've got domain, asymptote, range. Well, this is the same answer for every log function we graph. What's the range always? Yep.
-50 and positive.
It's always going to go up and down forever. So without even making a sketch, we figured out everything they wanted. Now, the first part of the question was sketch. Okay, but we have everything else done. Okay, so let me type that in so I can use the table. I'm going to do log 3x plus 5. Log 3x plus 5 divided by log 2. All right, let's check negative. Well, actually, you can't really check negative 5/3, but hopefully you can kind of see that it looks like it's about negative 1.6. That's where the vertical asymptote would be. And this should keep going like that. All right, if you wanted to check something really close to it, I mean, if you type negative 5/3, you should get an error, which we do. Now type something a little bigger. Instead of negative 1.66, type negative 1.65, and you should be down, you're down at negative 4. And if you go even closer, negative 1. Just type that in. Now we're down at negative 9. Okay, so it is going down. All right, so we've got those points, that's fine. Let's do 0. That will give me my y-intercept. 2, 8, 10. So those are the points that I would sketch. All right, so we got negative 5/3. Let's put that in. About right there. There's our vertical asymptote. 0, 2.3. We've got 2, 3.5. 1, 2, 3, roughly. 8, just under 5. 8, 1, 2, 3, 4, 5. And 10, just above 5. Okay, good enough. And remember that it's going to come in and drop off at that asymptote. Yeah, there's your sketch. Okay, question on that? All right. So the last thing, you're going to have one question in the homework that asks you to calculate the intensity of an earthquake. If you ever see on the news, like they say a magnitude 4.2 earthquake or something, that's the formula that they're using to calculate it. So the formula has 3 variables in it, and that will calculate R, which is the number on the Richter scale that they use to describe it. So they'll give you the A, the T, and the B, and you just fill them in. Okay, I just wanted you to see what the formula is. So R is the magnitude. That's usually the number that you hear reported that describes the earthquakes, how powerful it is. And the thing to notice in this formula is it has a log in it. So if you compare the intensity of the earthquake, if you go from a magnitude 1 to a magnitude 2 earthquake, you might think, oh, it's just a 1 to a 2. Well, it's a factor of 10. It's kind of like pH in chemistry. If you have something that jumps one number, that's 10 times more acidic or basic. And then when you go from a 2 to a 3, that's another factor of 10. So now if you compare a magnitude 3 to a magnitude 1, magnitude 3 is 100 times more powerful than a magnitude 1. So it's a big difference when you just go up one number, okay? Because it's a logarithmic scale. Another factor that they'll give you to calculate is A, which is the amplitude of the vertical ground motion measured in micrometers. And B is a factor that accounts, oh, I forgot T, I'm sorry. T is what we call the period of the wave. We're going to study more about waves when we do trig. But the period of a wave basically is how fast it oscillates. Something like that compared to something like this. the graph in red would have what we call a faster period, or a faster cycle to it. So they'll tell you the period of the wave in seconds. Think of like if you were in the ocean and you count waves going by you, how long does it take for a wave to keep going by you? That's like the period of the wave. And B is a factor that accounts for the weakening of the wave. I don't know exactly how they can figure that out, but imagine like if you were to drop like a big object in a lake, that wave really keeps spreading out and it doesn't weaken super quick. That's why if you've got a boat like really far away from you and they make a wave, it's probably going to reach you if it's a good sized wave. But then imagine dropping a big object in a pile of sand. It hits the sand, you'll see a crater, you'll see the wave, but it pretty much dies because the sand is different than water. And so B accounts for the weakening. Any question on that formula? Okay. So that's homework for tonight. 293, that's on the, I think that's the power model. So you will need a calculator to find the power model. And page 301, that looks at the second part of what we did. A little bit with transformations on logs, change of base formula, graphing, and then there is a Richter scale problem. Somewhere it's between 32 and 52. It's one of those. So tomorrow, the plan is just to review everything we did today. The homework is due tomorrow, but there won't be any new assignment tomorrow.